Good afternoon, everyone. My name is Drew. I am a PhD student at Monash University under the supervision of Professor Habui and Professor Yang Nguyen. Today, I'm going to talk about a numerical approach for simulating the liquefaction and associated large deformation of saturated porous media under earthquake. As you know, earthquake is a natural disaster, and look at the figure here. You can see there are many earthquakes occurring around the world since 1900. And the case histories illustrate the damage caused by earthquake. We could not do anything to stop the earthquake. The only way to mitigate this natural disaster is evaluating and predicting the consequences of such disaster by using an advanced computational approach capable of handling large deformation. And this is the motivation of my research topic. Here is the general framework for the SPH simulation of large deformations of the seismic response. So here is the general fully capable SPH framework for to analyze the coupling interaction between the pore water and the soil skeleton under rapid loading of the earthquake. And additionally, we use an advanced bounding surface plasticity model to capture the cyclic response of the soil under earthquake, including the liquefaction response, the degree of the effective stress, and the buildup of excess pore water pressure. We also developed the SPH free field boundary and the SPH complex base boundary to effectively capture the wave propagation and the wave dissipation during the earthquake. So verification and validation studies have been conducted to demonstrate the effectiveness of our proposed framework. So here we compare our solution with the seismic response observed at the field during the real earthquake. And we also compare our solution with the shaking table test available in the literature. Here we compare our solution for the excess pore water pressure, the acceleration response, and also the soil deformation. We further apply our proposed framework to solving the boundary value problem, including the earthquake-induced retrogressive landslide, the earthquake-induced dam failure, and also the deformation of a retaining wall here. My conclusion here is that our proposed framework is a robust tool for predicting and evaluating the consequences of the boundary value of the sheltering problem under earthquake. And my poster is in the corner, so hope to discuss with you more later. Thank you for your listening.
Hello everyone, welcome to my presentation. So I'm a PhD student at Monash University under the supervision of Professor Habui and Professor Yang Nguyen. And this is my topic, modeling wetting-induced slope collapse of unsaturated porous media. So as you may know, wetting-induced slope collapse or rainfall-induced landslide is one of the most common serious natural hazards for hilly slope due to prolonged or heavy rainfalls. It may suddenly occur with high swelling speed, posing threats to human life and properties. So for us, like academy or geotechnical engineer, what can we do to minimize this problem? So among various methods, the early warning system is considered to be one of the most promising ways. And in this system, it requires a model that can predict when, how, where that this disaster occurs. And then that is what we did. So first, we starting from consider an RPE of unsaturated porous medium, including solid, water, and air, and then we apply the multi-phase mixture theory to establish the governing equation for each homogenization phase. And then after that, we're using the single layer approach to combine all governing equation to establish a unique governing equation for entire system, including porosity, steep change, solid flow, and the motion equation. And when we want to solving this equation, we need several components. So first here is a saturated constitutive model. This is when we want to describe that when wetting happens, how after soil shear strain reduction. Second is soil water carrier curve and water permeability function. Basically, it demonstrates that when wetting, how that water infiltrates into the slope and is the seabed flow fast or slow. And finally, to solving the governing equation, we need to using a numerical method, solving the spatial derivative. Here we're using the HBS method. So the HBS is the continuum mesh-free method, in which particles carry field variables and move with the material velocity. So after we complete the framework, and then when we bring it to reality, we often seeing like the limited data. So that's why we also develop the ground modeling. Basically, if we have some of the borehole data input, and then we're using the optimization to basically reconstruct entire soil profile, and then to do the simulation. So this slide here showing you that the field scale prediction. So we're doing the validation again, the field experimental data from Ascari Design 2009. Here is slope, he has some of the sensor setup, and then after the test, he has some of the failure area recorded. And this is the simulation. If you look at it, the bottom left, at the bottom here, we start the simulation, the rainfall infiltrate, the water accumulating and causing collapse. You can see the failure area also can predict it, similar with the observation from experiment data. So if you look at on the top here, that's where our result expressed with the experiment data. The result captured quite nice. And finally, the displacement evolution. We were able to capture which is the stable stage or the collapse stage. And from there, we can using this information to doing the early warning to make the people help you evacuate our dangerous situation. So not only 2D, we also present 3D at a poster over here, and we can using for the real application. Thank you.